All right, so welcome everyone back. So the next speaker today is Nicola Capacci from the University of Zurich, and he will talk about an algebraic approach to scalar field theory on manifolds with boundary. Please.
Yes, thanks a lot, and actually thanks for the invitation. I'm really glad to give this talk, especially right before the talk of Eugene. I think it will make a lot of sense, especially given the fact that I don't plan to do something super weird, but if you're not very comfortable with factorization algebras, you will definitely, well, hopefully get an appreciative understanding of how to use these things. Emphasis on ongoing, because there is a number of questions that we still don't understand. But let me set up the problem that I'm sure is a problem that most of us are interested in. So as you do field theory, let's say in the most categorical way possible, well, there is the functorial field theory way to do the things. You have a picture that looks like this, some way to understand that you evolve quantum states that live on the boundary along cobordisms that are one further dimension. More precisely, this defines some monoidal functor from some bordism category to some category, typically Hilbert spaces. So here the fundamental objects are states, and the upshot of doing things in the functorial field theory is that it allows you to compute the partition function by cutting and gluing, which is a very complicated procedure otherwise. That is to say, like, suppose that you want to compute the partition function of a weird surface, like a genus 2 surface like this. Well, this is the same as sorry about this. So this is the same as saying, well, I first compute the value that my functorial field theory assigns on the two pieces, and then I glue them back together in this way. As you see, I'm not an artist, so don't expect much. So what's the other way to do field theory? The other way, instead of states, you talk about observables. So the fundamental object for observables, you're in a situation like so. Let's say that I have some fixed manifold. Let's say this is my X. It's a bit shabby. Let me make it a bit bigger. So I have some manifold X. I'm interested in some correlators, so I mark some points X1, X2, X3. And the object I'm interested in is computing the expectation value of something like this. Now, the object on this side is something called the factorization algebra, which perhaps we have not seen defined yet. So let me say very quickly what a pre-factorization algebra is. On X, well, okay, so first of all, it remembers about local observables, but further than this, it remembers about how to multiply local observables. The picture is that I can surround my point observables by disks, and I have a multiplication operation that's parameterized by disks. And so I can first multiply, phi1, phi2, and then multiply phi3 and get this object here either way. The actual object that this parameterizes, well, okay, so X, it assigns for each, let's say, open inside X, it assigns some object. Let me say that I'm interested in pre-factorization algebras on X with target chains. It assigns some object f of u, which is a chain. And given a sequence of embeddings, something that looks like this, I have some Cauchy type property. So I have a map f of u, f of v. But further than this, if I have a disjoint union, so I have u1, u2 disjointly included into X, then the piece of data the factorization algebra assigns is monoidal. So it assigns, I surely don't have enough space, but let me put it here. So f of u1, u2 is f u1, Fu2. I'm sorry if I already run out of space. Okay, so without any Cauchy condition, importantly, and because this is a prefactorization algebra. So these are the two ways to do things. It's well, okay, so it's a well-ish known fact that if you're interested in topological field theory, these approaches are essentially equivalent. From a, like, you can mess around, but essentially what you're doing is the same thing. We can even, okay, so this is work of a lot of people, such as Luri, Claudia, Damian, Ayala Francis Tanaka, and many, many more that I couldn't possibly cite. And the result in the topological context is that you get a diagram such as this one, which is a diagram of equivalences. But it's a diagram like this one, because the proper diagram, should it exist, it actually holds a lot of labels that wouldn't make the understanding of the diagram any easier. But I can tell you what the maps look like. So as you go from this functor category to algebras, you're using the fact that En is essentially this scan. As you go down from the functor category from this scan, oh, I should say T stands for target. I don't really care what this is now. As I go down from these functors disk into target, here I am evaluating a factorization homology. So do something like this. So this is a factorization homology. And down here I have the category of homology theories on n-manifolds. This morphism here utilizes the cobordism hypothesis. Specifically, going up means evaluating the partition function at the point, which yields an object inside this category, which I should say is the one that we saw this morning, the higher the category of the higher Morita n category inside the target. And finally, we have just one last morphism. I believe this is the morphism that Claudia defines in her thesis. And the question that we are interested in is to try to understand whether a diagram like this or a situation like this holds for non-topological theories. So what we will do now, I mean, it's not, so what we will do now is change this category of disks, which is a category of topological disks, with something else that will then change consequently our category of manifolds and our category of Bordisms. Several of the morphisms are still sort of well defined. There is an abstract nonsense version of the cobordism hypothesis that's fleshed out as much as humanly possible by Luri. There is a version of factorization homology by Ayala Francis Tanaka that holds on disks with any structure. And so the problem really is this direction here. On top, well, you won't land in EN algebras. Sorry, in this category of algebras, you will pick up something else. For instance, like it's a result of I believe maybe Costello, that for conformal theories, you pick up Calabi-Yau objects. But okay, so in principle, if you change appropriately your category of algebras, you could also recover these two errors here and here. The problem is this error of Claudia that I believe uses additivity. Like this error here uses EN additivity. Which won't work if it's not topological. So something else must happen. Now, understanding this problem in general is way beyond what we can possibly do. So our idea was much simpler. It goes like so. Let's pick a very simple theory, and let's try to work through this diagram. Specifically, what I'll be able to do today, I'll pick the simplest possible quantum field theory, scalar massive, non-interactive scalar field theory, and I will show that there is a gluing statement for the factorization homology of this theory. And this is as much as I can probe into this diagram. We have many more ideas as to like what goes on behind it, but I think we'll dedicate this to the discussion afterwards. I think I'm looking forward to this. Okay, so our first goal is to change our disks. Stop me if you have any questions, by the way. Okay, so our first goal is to change our disks. Let me give you a rather long definition. So let me define a category of Riemannian Cartesian spaces with boundaries and corners. So, okay, so first of all, okay, so it will be, okay, forget about this first question, let's, the first sentence, let's return to this later. So a simple object inside this category looks like so. So it looks like some quarter portion of a Cartesian space. It's equipped with a Riemannian metric with a choice of orientation. These two are compatible with each other in a certain sense. Here I just write a simple condition that the volume form induced by the metric, I want it to be the integration measure for the orientation. In reality, I specify both the metric and the orientation in terms of bundle reductions, and I want these bundle reductions to commute with each other such that when I glue, all these things work out. But this is an entire story. And okay, so either way, my objects are spaces with metric and orientation and boundary, and I got a lot more structure that remembers about boundaries and corners and all the complications that come with it. So first of all, if I, okay, so my object is canonically in this presentation, I have, if I forget about one of these Ks, oh, sorry, there should be a plus here. So if I forget about one of these Ks, I have an embedding of my space without that boundary direction onto my original one. And I pull back the metric and I declare, the metric on this piece of boundary to be that. And of course, like I have this object, I also have the object delta I, delta j, u, that forgot about two direction and then pulled back the metric. So what I require is colors. And the way that I induce, in the way that I ask for colors is I say, well, okay, for each of these directions where I forgot about the metric, I choose an epsilon in which I prolong in the interior. So let me give maybe an example. So here I have the half plane, my, so let's call this u, my delta u is just the boundary on which I left the metric. Here I choose an epsilon. So for instance, I choose this epsilon here. And then I consider this Riemannian space with the product metric. And I ask that the canonical embedding so that there is an embedding that trivializes that boundary direction and also pulls back the metric, meaning that I have a color in this direction. When I have a corner, something like this, so this is my del 1, let's say u, this is my del 2u, and I have two epsilons. I must ask that a certain diagram commutes in the intersection. This is like, if you work it out a moment, it's very simple. Okay, so the other thing that you need is a poset stratification. So my opens know about the boundary by this map. This map here maps a point X to 0, 1, 2, etc. 0 if I'm in the bulk, 1 if I'm in a boundary, 2 if I'm in a corner, and so on and so on. My morphisms pull back the metric and collapse onto boundary and corners. So it means that I have just a function that does this, that commutes this diagram. In essence, it means that I can map a line onto, let's say I can map a line onto a plane as much as I want, but an half line, for instance, onto an half plane, I can only map if I map this point here. So this point in the boundary. Okay. So if you want this, so I could also Yeah, let me just move on because I don't have a lot of time. As far as nomenclature is concerned, well, okay, so I can put K up here to say I have codimension at most K, and down here to say I have bulk dimension N. And most importantly, I can
There is a short question from Eugene.
Yes, please.
Maybe.
Mm-hmm.
Just a quick question. Are your the morphisms, are they always embeddings?
No, they pull back the metric, but this means that they can either be closed or open embeddings. Then I restrict to open embeddings.
But you mean closed like a line in a plane?
Exactly.
Sure, but that's still an embedding, right?
Sure. But that's okay. That's as much as I will want anyways. In fact, in a slide, I will even forget about closed embeddings. I will only want open embeddings. In reality, you want to keep all of the morphisms because there is a general procedure by which you make, for instance, generalized smooth spaces. And if you want, this procedure follows in analogy to that one. And as you make generalized Riemannian spaces, you I really should go much faster. You say my site is generated by open embeddings. I have all these other morphisms, but to generate object, to generate the category of generalized spaces object-wise is sufficient to do it with open embeddings. We can talk about this later if you want.
Sounds
the
good.
reality is that I have no need for any other type of morphism. So, okay. So,
if it's okay, then Pele has also a question, a short question.
So what do you mean by taking the free symmetric monoidal category on this thing?
Oh,
do you do this as an operad and you take the symmetric monoidal envelope or something?
Thank you very much. Here, I mean, I take exactly, I pass it through the free opera, construction. What I end up having is a category with the disjoint union of these objects and the maps between them.
Okay.
Yeah, that's the essential, like how you make the standard category of disks. You know, you just start with one Rn, you make the free symmetric monoidal category on this, and you make the category of n disks. Okay, so so let me just say my category of open embeddings is R disks. And a fact that we can show is that this defines a nice geometry on which I can make spaces. So let me say what it means in practice. So in practice, given any site, you have this, well, more well known is that given any site, you have a reflective localization between the category of sheaves and the category of pre-sheaves. S stands for site here.
So I'm sorry, Nicola, there is Pele again has a question.
It's all right.
We cannot hear you. You have to. Sorry.
I'm sorry, very quick. So do you mean, so geometry in the sense of Lurie, do you mean like in the sense of DAG5?
In the sense of, you have to remind me, I mean it in the sense in which I say after. I believe that it's probably the same. This more precisely, I mean that in Riemannian disk is the site with open embeddings, and the structure of a site extends well to the category of Riemannian Cartesian spaces. And so Riemannian Cartesian spaces is a site where, you know, on admissible morphisms, the admissible morphisms are the open embeddings.
Okay, so it's, and actually, so it's called a pre-geometry.
Is a pre-geometry.
Yes.
Thank you.
Okay.
Yes, actually, you're correct, because otherwise it adds algebra. So, yeah, sorry, yes. Yeah, sorry, let me move on a bit fast. So a bit less more known is that the reflective localization between sheaves and pre-sheaves descends also to diagrams. In particular, for me, this means that I can identify the category of Riemannian manifolds inside this category of sheaves. Here is why. Let me pick X. Let me suppose that I have a good understanding of Riemannian manifolds. And let me take the category with open embeddings. And let me take a chart of X. And let me express this data as a functor that is a diagram that lands in Riemannian disks. This is not very complicated. Like if I have a circle, I can just choose a chart like so. And then I literally write it out. U1, U2, let me call this V, W, and I can write a two-step diagram, V1, V2, into, sorry, into VW, U1, U2. So any atlas gives me a diagram like this. If I project down this diagram onto sheaves, this gives me some object. Now, if I choose a different atlas, I can take the refinement of these two atlases. So if I choose a different atlas, AX, I can take the refinement, let me call it like so, and I can look at, and I can form a span like this in my category of diagrams of Riemannian disks. This span gets equalized to the identity by this reflective localization, hence I pick up a unique object in sheaves. So this means that I can understand my category of Riemannian manifolds, actually at the end, as a full subcategory of the category of sheaves of Riemannian disks, which is quite nice. I mean, it's also obvious because atlases are manifolds are equivalence classes of atlases. Okay, so we understand geometry. Let's do scalar field theory. I'm not so interested about the target. I require that I have a nice abelian category of infinite dimensional vector spaces. Later, I also require that like its internal category of chains has got enough projective, so it's got projective model structure. But yeah, I'm not super careful about my target, unfortunately. So scalar field theory works out like this. You have your manifold X, and your fields are just real value functions on X. And the Lagrangian reads d phi star d phi plus m squared star d phi star phi squared, where star is the Hodge star. And it utilizes the orientation and metric on the base. So if I look at this locally, I claim that scalar field theory is controlled by the sheaf. Let me call this EL0, it stands for the Euler-Lagrange critical locus. I land in chains, but I really want to think of this as L-infinity algebras. And in fact, I use a lot of L-infinity algebra language. So what do I map? I map a collection of disks U to the two-term chain complex, B1 delta plus m squared, shifted by -1. I think of this as an abelian L-infinity algebra because if I add the interaction, this differential here that I called B1 has got B2, B3, B4, which are the higher brackets of the L-infinity algebra. And note here that I have used the shift. So I'm not in the standard shift convention of L-infinity algebras, but this should be still okay. So, okay, locally my moduli problem looks like so, but it is the case, so an easy thing to see, that this functor is a sheaf of Riemannian spaces, which means that I can pick up on X the moduli problem as a colimit, which means that on X, any choice of atlas any choice of atlas, so I have up here, tells me the moduli problem on X as a colimit. And more generally, it tells me that I can extend naturally Riemannian disk, that I can extend naturally the assignment of the moduli problem. Chain up, here I have up, of course. Let's see, sheaves of Riemannian disks. Here I use the unit embedding. Here I have Riemannian manifolds. And okay. So this is my moduli problem on X. I can also explicitly write it down. I mean, it looks like before, but with X. Delta plus m squared. So this delta is the Laplacian. Okay, so let's get an appreciative understanding of this moduli problem. Let's now, instead of a generic Riemannian manifold with boundary and corner, in reality, I use the theorems from analysis and I can only do boundary. Corners, I can try to smooth them out, do all sorts of things, but let's be precise. So let me fix a manifold with boundary, and let me pick M non-zero. Otherwise, the moduli problem is entirely different. So as a colimit, I obtain this, and I'm interested in the cohomology of this two-term chain complex. The reason should be well known if you're comfortable with BV, is that at level 0, I pick up the critical locus, so like solutions of the Euler-Lagrange equation. At level 1, I have very mysterious things. BV cohomology in level 1 is a bit weird, but in this particular case, I get that it vanishes. The relevant theorem from analysis is that if I look at this problem over here, so the problem of finding solution with a given boundary condition, if my boundary is empty, I have the zero solution. That's it, because my mass is non-zero. If my boundary is non-empty, then I have a unique solution having posed either a Dirichlet or a Neumann boundary condition on the boundary. And in particular, I utilize this fact quite a lot, that I obtain extension maps. So I have, this is for Dirichlet boundary condition. So I have an extension map that takes a boundary section into a section of the bulk, and it has the property that if I take that section and I restrict it, things that are in the fixed point of these are precisely the solutions in the bulk. Okay, so what does it mean? It means very, very precisely that I can express a special deformation retract from ELB, can express a special deformation retract from ELB to the cohomology. So, and the special deformation retract gives me a form of the minimal model, if you're comfortable with the notion of minimal model for L infinity algebras. It is a diagram that looks like so. And I will use this later. So maybe I'll yeah, let me not prove this. Okay, so we get sort of an understanding of the minimal problem. I mean, the minimal problem is assigned locally. So it's assigned locally and also locally over X or over B if you want. But I only understand it globally because this minimal model, I only have it over fixed B. Either way, I can understand observables locally. Well, how do I do this? If you notice here, I have my original moduli problem. I'm just post-composing with Chevalier-Eilenberg cochains, because I think of these chains here as abelian L infinity algebras. And only in non-L infinity algebras, I have the model for functions for this is, well, Chevalier-Eilenberg cochains. For if I am abelian, it just turns out that I have to take dual and the symmetric algebra. So what does it mean here? I have here charts, which I define by declaring this square to be the comma square. This category is much easier than you expect. So it just its objects are disks. U now is a disjoint union of disks embedded into X. I have and morphisms are this way, but note that these are like Rn times Rk plus, you know, like they are a disjoint union of objects. So this assignment, it takes U, let me put it down here maybe. So this assignment, it takes U to the completed symmetric algebra on EL0 U. The idea being that it gives me a model for, so if EL0U tells me my states on shell, this gives me a model of functions on shell, sorry, observables on shell. I can also make a diagram like this where I replace, so if instead of Riemannian disks, I replace with, so if instead here of Riemannian disk, I replace with another copy of sheaves, then I obtain OpenX to DG algebras. very simply, where now I don't have necessarily contractible things. But this is not so, okay, importantly, this morphism here, suppose I even forget I land in chains, is a factorization algebra like I originally said, but it's even more because my functor is a monoidal functor, and I extend it. Okay, so this is not a Cauchy as I go from here to here. It's not a Cauchy, but as it turns out, it's an homotopy Cauchy. So this let me saying two things. First of all, that locally observables make a Riemannian disk algebra of scalar field theory, and secondly, that the observables on a given space X are exactly the factorization homology of this Riemannian disk algebra. If you want, this means that let's see, like before, I had a extension for fields. Now I have, so let me take Riemannian disk here, observable 0. Let me land in chains. Here I have sheaves of, oops, sorry, going down. Sheaf of Riemannian disk. And I have Riemannian manifolds compact here, that this is a homotopy, the way that I extend this out. Okay, so I have, so this specifies my moduli problem globally, my algebra of observables locally, and also a way to multiply this algebra of observables, but this is very standard from Costello-William. By the way, I should just say this, if you ever were curious about what the descent, wise descent, because like factorization algebras, if you've read Costello-William, they're required to descend on wise cover, is because this is the largest wise cover. And so just a way to identify this with some type of, with the image of a factorization homology. Anyways, so now we have this moduli problem. We want to quantize it and to produce the quantum observables. Now, quantization is controlled by a symplectic structure. And if I have fixed a Riemannian manifold, I can provide a bilinear pairing over B. The mass mean to R shifted by O minus 1. And I map phi1 dagger, phi2 dagger, sorry, phi1 dagger, phi1, phi2 dagger, phi2 into B, mu B, phi1 dagger, phi2 dagger, phi1. And so I have this pairing here. And this pairing defines a two-form, BEL0, which is constant coefficient. And it's easy to check that as a map from vector fields to one forms on my moduli problem, this is injective. But that this form is closed if and only if the pairing is, well, if you want, cyclic with respect to, let me put it like so. It's cyclic with respect to the differential. So it satisfies this. So if you remember, B1 is delta plus m squared. The m squared term, whoops, the m squared term drops out. So the only thing I care about is that, okay, that, okay, so if my boundary is empty, then this is the statement that delta, that my Laplacian is self-adjoint. With respect to the L2 pairing. But if my boundary is non-empty, then I have, let's see, oh, thankfully I have another page. So if my boundary is non-empty, then I have an obstruction. Let's see it here. I have something called, well, there's the Green's identity that reads like so. Let's see, del phi minus phi mu t. U. And now I have, so the boundary is the inclusion, the boundary in B, and D D does star. Sorry, let me check this. I should have this here. Takes the normal derivative. So D, sorry, let me write it like so. From omega 0 B to omega 0 partial B, takes phi to the normal derivative of phi along the normal of the boundary. And psi d phi minus phi d psi. So in general, I have this obstruction to my cyclic structure being my structure being cyclic, and this obstruction will not work out. And Eugene will tell you later on what you can do at the level of fields. Instead, what we do is we say, let me just declare a very convenient algebra of observable. And this algebra is magically P0 because I have chosen everything to work out perfectly. So first of all, let me talk about my observables. So first of all, my observables should be inside, well, okay, so the ones, the generators should be inside here, which has got distributions, but instead of distributions, I choose bump functions. So my observables, this one is, like, let's say I'm like here, it's measuring the average value of my field along, a bump function in the bulk. This is doing the same for the anti-field. These two observables are measuring average. So if this is my boundary of B, here I have B, are measuring average value of the amplitude. And if, yeah, so this is for Q, of the amplitude and the flux of the field through the boundary. Q0 has to be this way because this is the differential in Chevalier-Eilenberg. I'm just restricting it to this class of observables. While this bracket I declare to be this way. And if I declare to be this way, I have a monoidal functor that lands me in P0 algebra of very convenient observables. And this monoidal functor I can lift from P0 canonically perturbatively in H bar to BD0. And like Costello-William, with a very minor modification here, I have that my classical observables and my now quantum observables are just a deformation of each other. In fact, with this lemma, I can prescribe the star product of observables onto my manifold. But let me take questions later because I really want to finish, sorry. But instead, okay, so this is my deformation. And like with this, I get my quantum disk algebra that looks like so. And the factorization homology statement from before applies so that I can talk about quantum observables on a given space X as the homotopical limit of the diagram, chart X. Let me say, yeah, no, it's all right. No, let me say X now, though, is a manifold with only boundaries, possibly. So chart X to chains. Observable 0, and this is precisely what I expect. So this gives me classical observables on X tensored with the CH bar, and this is Chevalier-Eilenberg of Euler-Lagrange critical locus, so just evaluated on X. Okay, so given this quantum algebra, this isomorphism onto my classical algebra, and especially the minimal model I used before, I can describe this diagram. Now, what is this diagram doing? It's taking a quantum observable, using this isomorphism to map it onto its classical version. And then, okay, so remember I have EL0, homology of EL0 from before. I had an extension map and a restriction map. I map the extension map through the functor of Chevalier-Eilenberg cochains. I obtain a map that goes this way now. And I restrict my convenient choice of observables, this extension map to my convenient choice of observables. Now, my quantum observable alpha that is mapped to alpha C, I map it down through the dual of this extension. I get now something that I call this way. This is, if you want to understand it, is I have projected my quantum observable onto a function of the Q's of the boundary, such that if I tell you what Q is on the boundary, you can evaluate this, and it gives you a number. And in fact, I gave you 2 examples of such a procedure. So this is the quantum correction. This is just evaluating the classical observable. So the classical observable psi1, you know, measures the bump function, so the average value around the support of psi1 of the field, but the field is just the extension of Q. Okay, I have very little time, so let me say this statement, that this projection is, I can assign very, I can assign coherently to all spaces, so that I get a functor that looks like so, that attaches to a manifold with boundary, the algebra of quantum observables, and also the projection onto these complex boundary values. And 2 things. So this fact here, the fact that this functor is monoidal, but also the previous fact that begs the idea that probably this is the delooping of something that's higher, because my category of manifolds, well, okay, so if I restrict to connected objects, then I have a groupoid. And so, like, if I look at, you know, all the manifolds that have given a given boundary, I get a groupoid and then a bunch of like bubbles and so on. So I get a very interesting statement here. I think the beginning of something. But more interestingly, the gluing statement, so that I can get to some point. I need to define, well, okay, so I use very much, the reason that we chose scalar field theory is because, so Santosh, Pavel, and Konstantin, maybe is here, did the functorial field theory for scalar theory in 2D, I believe. And they had this gluing lemma figured out for the partition function. So the story goes like this. Suppose that I have some surface, or some, let's say, well, higher dimensional surface is just a Riemannian manifold without boundary, and a color gluing that divides B into B1 and B2. So let me take the value of Q here and extend it to, using the Helmholtz extension, to the 2 sides. And then let me compute the normal derivative. Sorry about this. Let me compute the normal derivative on this side and on this side, and let me sum them up. So I compute the normal derivative. I call D, so D1 E1 Q1 plus D2 E2 Q2. Sorry, there is only one Q. So E2 Q. This defines an operator from omega 0 y to omega 0 y. This operator is called the Dirichlet-Neumann operator, and sometimes defined D of y. So it maps me Q to this value over here. And K is the integral kernel of dy inverse, which is shown to exist. And then I have this gluing lemma that tells me about the Green's function on either side, and this integral kernel in the middle. Importantly, because I have this gluing lemma, I have a cutting statement, which is the last thing I'll say, I promise. So I have this cutting statement that goes as follows. Like I define the operator for the Green's function, I define an operator for this K, and I define a pairing. Then I have the cutting statement. So the cutting statement says this. So let me put my picture up here. I have y, b1, b2. And okay, so let me take alpha an observable here, beta an observable here. And so I take alpha, beta. Here I multiply them. I get alpha star beta in the multiplication of the factorization algebra. Here I project them down. Let me use bracket notation, even though I have no actual use for this. So I project them down to alpha and beta. And then I pair them together. And here, what do I do? Well, if my manifold is got no boundary, then the extension map evaluates at 0, because that's the only solution that I have. And so, if you want, H tilde of S, if S has no boundary, is just CH bar, canonical. And so my projection with S lands me in CH bar. This diagram commutes. meaning that I can compute correlators by a cutting procedure. More generally, I think, so more generally, yeah, I mean, it's, I am out of time, but so like it's very easy to see if I consider, so let me say, for instance, I'm interested in like some smooth out 2-point function, C1, C2 here. So the statement is that del G of the entire surface, C1 hat, C2 hat, is del K of, I should check a sign, sorry, I should check a sign, I think this is plus, but I now forget, of the dual C1, 1 and 2, C2. Like so. So this is the easiest example of this cutting statement. Okay, thank you for your time. I think this is as much as I wanted to say, but I really do want to talk about this. So I hope that you come to the session afterwards, because there is a lot more that goes on here. Like you can see this as, okay, all factorization homologies, even the structure one, satisfy some Van Kampen theorem that says, you know, like, let me use this picture. Let me just abuse this. And let me call the sigma, the color gluing. So all factorization homologies satisfy a Van Kampen statement that looks like so. And this is a statement of Ayala Francis Tanaka. So we are witnessing something like this, but not exactly. What we are missing out on,
maybe I start
a new one structure. Yes, sorry. And
yes,
that's everything that I wanted to say.
Yes,
we can talk about this later. Thank you.
Thank you very much. Thank you very much. So, okay, yeah, so you can always ask, of course, later in the gather, but are there any questions now? All right, so we have a question of Eugene.
Thanks for the talk, Nicola. It was very interesting. So can you go back to the slide where you have this special model of the observables where you introduce extra?
Oh, yes, of course. That's the most important slide.
I thought that was really interesting.
Yes, over here. Let me clean it up because, of course.
So do you have a sort of homological, like some sort of interpretation of this complex? It sort of looks like a cone.
So
bulk fields, boundary fields, and you have your Lagrangian inside the boundary fields, and you're taking the cone on that.
exactly, that was roughly the idea. I get, okay, so these are my ordinary observables, like the ones that I would attach if I didn't have any boundary, for instance. And this piece here is contractible. And this is something that I add on, but this choice is much stricter than you imagine. I must have this observable necessary to be closed under Q0. So what's Q0? Q0 is the differential on quantum observable, and so it's B1 dual. So that's a delta plus M squared dual. So if I imagine that I apply, let's say, I apply Q0 on some psi, and I evaluate this psi on a field value. So what is this? This is the integral on B, mu B, psi, and now I have delta plus M squared. I should say psi dag and phi dag, because Q0 decreases the differential, like so. Phi. Okay, so now what I must do is transport this back. So of course I get, okay, so let me just say, I get psi delta phi plus M squared phi hat at phi. So now what I must do is take this Laplacian and pull it to the phi, so that I can write my Q0 applied on the observable. And it turns out that, I have to keep an observable like this and an observable like this. So Q0 is fixed. And to have my DG algebra closed under the differential, I must add these observables. That's just the boundary being there, I have to add them. The bracket on the other end, the bracket, I don't have a super nice reason for. The only reason I can think of is that it's a very natural choice, except for this 1/2 that perhaps looks a bit weird, but it turns out that it's because of this, because of a symmetrization. And I just turns out that it has to be this way necessarily to be a P0 algebra.
Yeah, so I thought about a similar thing. I tried to, well, maybe we'll discuss this later, but do you have any indication of whether this construction can be lifted to interacting theories?
Yes, I do strongly believe this. I worked almost everything out for this. Yeah, talking about this though would have lasted me 3 hours. I didn't even bother.
Yeah, that's interesting because
Well, actually, I must say this. I assume that I can find, actually, yes, modulo the fact that I assume I can find solution of the quantum master equations.
fair, yes. Yeah.
Which is not so trivial, but yeah.
Okay, so maybe you guys can talk then also later on the gather. So yeah, just to see if there are other questions, maybe. No other questions. Okay, well then, so let's thank Nicola again for the great talk.
Thank you.
And so we will meet